Okay. So that people can find? All right, almost ready.
Okay, bye everyone.
Thank you, Jordan.
Pleasure. David, once you're set, just put your Sharpie away and say hello to Facebook one more time.
Okay. Okay. All right, back. Thanks. Okay. Okay. Boy, this is an interesting live stream behind the scenes. Okay, so for those of you who are just tuning in, this is a little bit of behind the scenes in Sanders Theater at Harvard University as we shoot a bit of material for CS50 for MBAs, an adaptation of CS50 at Harvard College focused more on a top-down approach to understanding technical material so that you can hold your own, so to speak, in a more technical conversation, say with an engineer, so that you can make more informed technological decisions when it comes to budgeting for something in terms of time or cost or the like, and generally just better understanding the technology around us, though not necessarily to the extent that you would get your hands dirty and actually build things yourself. I'm here with CS50's own Dan Coffey, Scully, Arturo, Ian, Jordan just left us, and all of you are online. Feel free to come and go at any point, and eventually, some weeks from now, we post a finalized version of this, so forgive any rough cuts. Good to go? What's that? Yeah, indeed. All right. So now we can begin for real. All right. Okay, ready when you are. I think so. How about from over here? Actually, how about over here?
Why don't you open up, David, to Ian's camera? We'll get the screen up with you.
Okay.
And then you can turn to Scully up with you.
Okay.
Say your first opening lines to Ian and then turn to Scully.
Okay. Let me just think for a moment. Okay. We'll be ready in just a moment, folks, if you're tuning in online. Thanks. All right. In 5, 4, 3. Going negative. So what is it? This camera, sorry. Hi. Okay, 3, 2. So there are so many ways to, no, wrong sentence. This is what you never actually see in the final cut. So what does it mean to program a computer? At the end of the day, programming is all about writing software, or coding, so to speak. And this means writing English-like syntax into a text editing program, something like Microsoft Word, but simpler, in such a way that the computer ultimately can understand the English-like syntax that you're writing. Now, it turns out there are so many programming languages in the world. Indeed, it can get completely overwhelming as to how many there are, and which one you choose, and when you should use it, and how you should recruit someone who actually knows a particular language. But nicely enough, there are some fundamental constructs, some fundamental ideas that underlie most programming languages, so that once you start to understand and pick up those fundamentals, can you apply that fundamental understanding to most any language in the world that you might subsequently learn. Now, there's certainly some technical differences among languages, and there's certainly some historical differences among languages, because the reason that we have so many languages is because humans are constantly getting better at writing software. Humans are constantly figuring out, oh, gee, wouldn't it be nice to have my language have some other feature so that it's easier for me to get real work done. And so as in the past, will you see this sort of layering of more and more sophisticated, more and more featureful tools being layered on top of the simpler of the tools. So today, like always, we'll sort of start down here, work our way up, and then realize hereafter, can you apply most of these lessons learned to yet other contexts still. So what are some of the constructs that you might see in many programming languages? Well, let me propose a few new vocabulary words: functions, loops, variables, conditions, and there's even more than that. And you might recognize, of course, some of these terms from different contexts, but what do they mean? Well, what does it mean to program a computer? It means to write some instructions that tell that computer what to do. Now, if I pretend for a moment to be that computer, albeit in human form, what kinds of things could you tell me to do if you were the programmer commanding me to follow your instructions? Well, perhaps here as I stand with 2 feet on stage, one of the simplest things you could command me to do by saying it verbally or typing it out for me is to say, move. And so if you were to command me to move, I might take a step like this. Now, that wasn't all that productive. I didn't make my way very far. But if you commanded me again to move, I might take a second step like this. But that quickly becomes tedious, telling David, move, move, move. I mean, that's not a particularly compelling way to program. So wouldn't it be nice to tell me to do something again and again and again, but much more succinctly? For instance, if you want to tell someone in the real world to do something again and again, you don't just keep saying it, presumably, again and again and again. You might say instead, hey, David, move 5 times. 1, 2, 3, 4, 5. And so more succinctly, albeit in English, can you get me to do something again and again and again? And that something is the same thing. And so in the context of a computer program, we might call move, the act of me moving from one spot to another, a function, a procedure, really an action, a verb-like construct that's just doing something. And a loop, meanwhile, as the word rather suggests, is this notion of doing something again and again, cyclically, so to speak. And even though I've done it thus far in English, saying David move 5 times, you can translate this intuition ultimately to programming languages, as we'll soon see. Now, meanwhile, a variable you might recall from a context like algebra, x or y or z. Now, it turns out in many programming languages, do you have variables as well? And it turns out you can name them in a more interesting way than x, y, and z. In fact, you might name a variable counter if you wanted to keep track of how many steps you have taken. So for instance, if someone commanded me, the computer in this story still, to just move forever, I could move forever, and this is not going to end well at the end of the stage, but simultaneously, could I create a variable in my mind called counter, or x or y or z, whatever, but counter is more descriptive, and I could keep track of how many times I'm moving while moving indefinitely. So counter is 1, 2, 3, 4, 5, 6, 7, 8, and we'll stop it at that point. But loops indeed can be infinite. They can run forever, for better or for worse. And as an aside, if you've ever noticed your computer kind of spiraling out of control, whereby the beach ball is spinning or the little hourglass or the like, it might very well be that your computer is stuck in an infinite loop, doing something again and again and again that maybe is deliberate, like a clock ticking forever. Sometimes loops can be good if they tick forever, but sometimes it can be a bug, a mistake in a program, as we'll soon see, that a programmer or a human did not anticipate. And so a program just keeps running and running and running, consuming all of your computer's resources or memory or CPU, and so you can't really do useful work on it. So loops can be both good and bad in contexts like that. And then conditions. A condition is a way for me to fix this problem. For instance, I might be told by a programmer, move forever, but if you're about to walk off the stage, stop. The operative word there being if. So irrespective of variables, I might just be moving and moving and moving and constantly checking. If I'm nearing the edge, am I at the edge? Am I at the edge? Am I at the edge? Oh, I am. And so I should stop. So if I am about to step off of the stage, I should stop. And so I can conditionally fix this kind of problem. And there's other constructs still, but this is to say ultimately that programming, or coding as it's commonly called, but the terms are pretty much interchangeable, is really just this process of translating this human intuition to a language, a textual language, a typed language often, that a computer understands. But there's many different ways to speak to a computer, much like we have so many different spoken languages, we humans, among cultures, among countries, within countries, so do computers understand different languages, so long as humans have kind of sort of taught those computers to understand those languages. Which is to say that when you buy a Mac or PC or whatever, it doesn't necessarily come with some built-in support for a whole bunch of programming languages. At the end of the day, it's going to understand binary, zeros and ones, and it's going to understand a so-called instruction set, whereby Intel or whoever makes the CPU inside pre-programmed it to understand certain instructions like add and subtract and move and load and so forth. But beyond that, it doesn't necessarily know how to do all that much with your human instructions unless you or some company, someone, has taught it to understand other languages. And so there are languages called assembly language. There's something a little easier to read called C. Then there were languages like C++ and Objective-C. And now there's Perl and Python and PHP and Ruby and Java and JavaScript and so many others still. But those are the results of humans over time writing software that can run on Macs and PCs that allows the computer now to understand not just zeros and ones, but higher level languages, things that humans can express much more pleasurably and easily than just zeros and ones alone. And these languages don't have to be textual, it turns out. In fact, when first exploring programming and programming languages more generally, I dare say it's more straightforward and perhaps a little bit more fun to actually sort of program by way of pictures, if you will, by way of puzzle pieces, we'll call them. So pictured here is perhaps one of the simplest programs you can write, and it's sort of entered into history as one of the most canonical programs you can write, demonstrative of what you might do in a language on your first day. And it just says, in this context, when green flag clicked, say hello world. Hello world being the buzz phrase that permeates most of programming history these days. This is a program that if you run it with the right software on your Mac or PC, will actually print the message on the screen, hello world. And what's nice is that it doesn't quite look like other languages, which we'll see soon are very textual and are a little arcane, a little harder to wrap your mind around because of so much punctuation that they tend to have. But we can explore for just a bit here programming by way of this graphical language called Scratch, via which we can see some of these same ideas, functions, loops, conditions, and variables and more come to life, so to speak, on the screen. So let me pull up exactly this program called Scratch. And there are 4 main areas to this particular program. It's freely available software, and you can also access it via the web, though I'm using a downloadable version here. And you'll see at left, perhaps most obviously, this cat who goes by the name Scratch. Scratch here is an example of a sprite, which is a term in the world of computer graphics that refers to some kind of entity, often some kind of character, that can do things, maybe move up, down, left, right, or the like. Meanwhile, on the right-hand side, there's this blank slate, this big canvas, this scripts area where eventually I'm going to be able to drag and drop some programming pieces, some puzzle pieces, in order to get this sprite to do something. And the pieces I can drag and drop and use are these here in the middle. And there's going to be way more than we even look at right now, but you'll see that they're categorized and also colorized by category. So we'll play around for just a bit with some of these sample constructs and see what we can't do. So in fact, let's see if we can't translate my human example to a cat. Hopefully that's not too much of a leap here. And let's see if we can get Scratch to do something quite akin to what I just did. So I know from having used this software before that I probably want to start with this events palette up at top right in the middle of the screen. And you'll notice if I zoom in, there's a whole bunch of puzzle pieces here, but only one that looks familiar thus far, when green flag clicked. What is that green flag referring to? Well, if we look at the stage over here on which Scratch lives, notice in its top right-hand corner, there's both a green flag, which is going to mean go, and a red stop sign-like thing that's going to mean stop. So those are going to be the 2 buttons via which we can start and stop my program. So kind of equivalent in your Mac and Windows world to double-clicking an icon to run some program. So if I now zoom out, notice I can click on and drag this when green flag clicked puzzle piece, and I can put it wherever I want. But much like in English, I might start at the top and work my way down and to the right. So I'm just going to let go. And you'll see now that it's plopped itself there. But it's not going to do anything because all my program is saying literally is when green flag clicked, it's kind of a cliffhanger. We need to attach some other puzzle pieces there. And the puzzle piece we saw a moment ago was something that looked like this. And here we have a new palette, the looks palette. There's so many purple puzzle pieces here, but I'm just going to go ahead and grab, say, one of them, which by default says hello. But notice, this puzzle piece, as I pull it over to the other puzzle piece, notice how this little white line appears sort of magnetically. It's because these 2 puzzle pieces, as per their similar shapes, want to snap together. And if I let go, notice indeed the puzzle piece does automatically connect itself. And if I don't want to just say hello exclamation point, but just more subtly hello comma world, I can just click in that white box and type my new text. So now consider what this is saying. When green flag clicked, say hello world. And it kind of flows logically, much like it did verbally as I was programming myself a moment ago. So let's go ahead and click the green flag. We're programming. We've just run the program. It has stopped. And notice he's still saying hello world because the computer, in many contexts, is going to take you pretty darn literally. And the fact that I didn't do what explains why he's still saying hello. Right? I never told the computer to stop saying hello or stop the program explicitly, and so it's going to keep doing this until I command it otherwise, as by stopping the program outright. Now, meanwhile, we had movement. So it's one thing to have a function, an action like say. What if we wanted to have Scratch actually move? So let me get rid of this purple puzzle piece and just drag it and let go. It'll just disappear if you drag it over to the middle. And now I kind of want to control the functionality of my program. So if I click on the control palette here, you'll notice a whole bunch of yellow puzzle pieces, one of which is forever. And that kind of connotes exactly what we're looking for, this notion of doing something cyclically again and again. It too wants to snap together when I let go. And now this seems a little unfortunate. Like, darn it, if this forever block doesn't leave me with just barely any room for other puzzle pieces, but no problem. The software that our friends at MIT wrote here for Scratch is going to automatically grow that block as needed once I start inserting new pieces. So I want to move. Motion sounds about right. And indeed, there we go, move 10 steps. Let me go ahead and put this inside. And notice this white line appears magnetically. I let go, it grows to fill it, and snaps into place. Let's just do 1 step as before, and we'll see in just a moment what I've done. Let's go ahead and click green flag. It's a little underwhelmingly slow, but he's literally doing what we told him to do, 1 step at a time. Thankfully, MIT had the foresight to make sure that Scratch can never leave the screen completely. Otherwise, it's kind of a frustrating experience. So you can always kind of grab onto like his little tail here. But notice the program's still running. So even if I drag him and let go, he is still forever moving 1 step over And so we'll see him going there again. Figured we should stop because of the light. Are you going? Can you see it in the shot? I thought Scully might be seeing it. Okay, you sure? Okay.
Can we just turn them off? Yeah, it's just casting a lot of light on the stage.
Yeah, maybe let's kill it because it's kind of distracting too. So for those of you who can't see this at home, we have some flickering lights up above, which... Sure, yeah, I think so. I mean, we can keep going, and then I'll just pause again when it's opportune. Yeah, I mean, yeah, if they can come up to redress or just kill it. So, any questions? No? Scratch, how did I first discover Scratch? Well, it turns out like 10 plus years ago when I was in graduate school, I was taking a class at MIT, cross-registered there, and it was taught by Professor Mitchell Resnick. And Mitchell was just at the time beta testing this software called Scratch that his whole team had been working on developing, especially one gentleman in particular, John Maloney, who we really got to know in years since. And what Scratch has been wonderful for is in after-school programs for younger students, say ages 8 and up. But we started using it here at Harvard some 10 years ago because it's wonderfully demonstrative of some of these programming constructs. And indeed, to this day, we continue to use it at the beginning of our college class, CS50 itself. Do we want to wait for them, or do you want me to just go ahead and we'll break when they come up?
Sure, let's keep going. They might come up in like 2 minutes.
OK.
Let's keep going.
OK, and here we go. But you'll notice a moment ago, I actually didn't really know necessarily where I was going to find the puzzle piece of interest to me. And even as I here too have to give some thought as to where these various puzzle pieces are, this is actually representative of how one might learn a new programming language for the first time. Once you understand some of the fundamentals, can you much more readily start to pick up what you need to know? Can you fill in the gaps in your knowledge? And thanks to Google and Bing and any other search engine out there these days, and any number of websites like Stack Overflow and Hacker News and the like, are there so many technical folks out there who can help you by answering questions for you, who have posted long ago answers to questions that you can rely on. And so indeed, the process of learning how to program these days, once you have a solid foundation in one or two or more different types of languages, really allows you to bootstrap yourself and figure out something new. So even as you might dive into an environment like Scratch, you realize and take comfort in the fact that you don't have to have known or seen every one of its features simply by pointing and clicking and trusting that you're probably not going to do much damage to the computer or to the program by just tinkering. Can you really start to explore? And indeed, that's where a lot of the fun of programming starts to come out. Now, with that said, this program seems to be arguably buggy insofar as it's kind of lame, if nothing else, that Scratch ends up walking pretty much off the side of the screen. Wouldn't it be nice if, just like my example where I was about to walk off stage, but thanks to a condition I didn't, can we prevent that kind of disaster? Well, let me go ahead and go into the control block, I think. And yep, indeed, there are not only looping constructs like forever, and then also notice repeat, where you can specify a finite number of times to do something again and again. Notice that there's this here, if then. And you know what? I don't want to move no matter what. I want to move, but then check immediately if I'm touching the edge. And here, too, I might have to do a little digging to figure out what this language can do. But I think if I go under sensing, touching. And notice touching currently says mouse pointer, which isn't quite what I'm looking for. I'm looking like for the edge, touching the edge. But sure enough, if I go ahead and click this drop down, I can change this puzzle piece to ask a question. Are you touching the edge? And this puzzle piece and the several below it are an example of what we might call a Boolean expression, named after someone by the name of Boole. And a Boolean expression is an expression, a statement, a question, whose answer is either yes or no, true or false, 1 or 0. And this is the perfect construct, therefore, to put inside of a condition the proverbial fork in the road or a branch so that you can decide based on that condition exactly what you want to do. Hey, that's okay. So for those tuning in at home, we now have our experts here to see if we can't kill those lights that are flickering. Oh, yes. And now a word from our sponsor, CS50 itself. Coming up in just a few weeks' time is the second ever CS50X Puzzle Day, a worldwide opportunity for students online, yourself included, to form a team with maybe 1 or 2 or 3 other classmates or friends who aren't even in CS50 itself yet, and to participate in not a coding contest, but a challenge of puzzles. Not quite puzzles like this, but puzzles in the sense of riddles and logic problems, none of which are going to require prior programming experience or great comfort with computers, just a heartening spirit, a spirit of collaboration with friends. And what you'll do, in a nutshell, is upon registering and upon the event itself starting online, you'll download a packet of puzzles, a bunch of printouts that you can then use on your screen or on paper, and then follow along with your teammates and see how many of those you can solve by the end of the weekend. Oh, yes, we'll mention that next. Are these on wireless, Dan?
What?
The lights? Is that why they're going crazy?
No, they're not.
Oh.
We think it might be the circuit itself.
That's not good. All right, should we keep going if it's not in the shot anyway?
She's gonna turn off the lights.
Okay. So meanwhile, we'll use this as an opportunity to plug yet another CS50 event. This one, CS50 Hackathon London, our second ever as well. We'll be joining with our friends at University College London, aka UCL, who are going to be wonderfully hosting us and a whole bunch of UCL students, a whole bunch of CS50X students, a whole bunch of CS50 AP teachers for an afternoon of programming and collaboration and perhaps a few snacks as well. The goal of which is really just to bring people together, whether they are on PSET 0 or their final project or anything in between or some other project altogether, to work on something collaboratively alongside classmates and staff. And if London is too far for you, and maybe you live a little closer to Manchester, UK, at the University of Manchester will we, just days from the London Hackathon, be hosting one there as well. So if you'd like to tune in to these or any number of events, would probably be helpful for us to toss a URL up online. Let me go ahead and open a browser and go to, can I remember our URL? Nope, CS50 Puzzle Day, pick a tick. There we go. So here we have CS50 Puzzle Day on pickatick.com. So if you want to transcribe this URL, go to pickatick with no K /CS50X-puzzle-day-2017. Meanwhile, if I can remember the other URL, hello. We have the CS50 Hackathon London on Pick-a-Tick. And indeed here, you'll see at this URL all the details you might want if you live in Europe. And you can go to pickatick.com/CS50-hackathon-London. And if, again, you'd like to instead come to Manchester itself, go to that same URL, but change London to Manchester. Those are currently the only 2 cities we support, so even if you want to try some other URLs, they're not going to work yet. But realize you're welcome to join us in any of these locations. Yes. Do we have any on the Facebook stream? All right, so we have a couple hundred folks who are tuning in right now. CS50's own Dan Coffey is taking a look through the Facebook feed to see if there aren't any questions you might like to ask in real time. Dan will read them to me. I'll respond wonderfully persuasively verbally here. Standing by. This is CS50 in the dark. What's wrong? That is not a question online. Wait, what'd they ask? Oh, I thought you said, what's wrong with my wardrobe today? So in CS50 for MBAs, we like to take things up a notch, leave the jeans at home, dress up a little more nicely, and so this is what you get. It allows, we think, students to take me much more seriously in this environment. We can talk about more sensitive subjects, like loops. What else you got? We're crashing and burning on the internet here. So, you from out of town? Yeah. Indeed, Arturo is from out of town, because not only is he from, was it Minnesota? Oh, Venezuela. He is also from Miami. And in fact, we met CS50's own Arturo Real in Miami at Miami-Dade College, where he was formerly a student. And he was taking CS50X by way of the Idea Center at Miami-Dade College. And so Arturo's now here in Cambridge with us, as is Lauren Scully, who's here behind camera 2. Scully we met in, I think, the Hauser studio while shooting CS50 live. And the fact that she was not turned off by our Muppeteering and other such things was a wonderful sign. Now she's with us full time. CS50's own Ian Sexton over here is actually from the UK. So every time we go back to, well, the one time we went back to the UK, it was a wonderful opportunity for him to reunite with some of his family there. And then, of course, CS50's own Dan Coffey, who's still looking for an actual question to ask, has been with us for several years. And it's funny, I really got to know Dan when he wanted to shoot in an aspect ratio of, I think it was 16 by 9. And I was like, Dan, I think we should go 21 by 9. And then he said, no, we should go 16 by 9. And what are we shooting in today? No, 16 by 9? Oh, 16 by 9. Okay.
When is CS50 live? When are CS50 lectures live? When should people be tuning in?
Good question. So CS50's lectures are live. If we have students here in person, it's not until the fall semester. So stay tuned to like facebook.com/CS50, where we will let you know in September when the next ones are. We're probably starting to run the risk of timing here. Should we just unplug and forge ahead? Okay. Okay, we're back. Thank you, Tina. All right. Okay, ready when you are.
No, hold on, we need another minute. We're waiting to patch those lights back in.
Oh, we can't just leave them off?
It's going to be very dark on that side of the stage.
Uh-oh, we see on Facebook that a lot of people are putting angry faces for this live stream. We know who you are. I think one such person was CS50's own Doug Lloyd. That is sass. Doug, you'll remember, is the fellow on CS50's team who eats his Snickers, is it, with a fork and knife? M&M's, but yes, touche. All right, we're back. Whew. That was a heck of a cliffhanger. Just like an episode of 24. Ready when you are. So all that remains is for us to drop into place the Boolean expression via which we can answer the question, are we touching the edge? So indeed, let me go ahead and drag and drop this blue puzzle piece right on there. And notice it too doesn't seem to fit quite right, but it's going to grow to fill. And now notice inside of the if condition, we have an opportunity to slide in one or more other pieces. So what do we want to do? Well, let me go to motion as well. And let's see, if touching edge then, let me go ahead and turn some number of degrees. I don't think 15 degrees is going to do it. See, notice that's a bug. The cat is still going. Let me go ahead and hit the stop sign there. Actually, let me rotate him a little bit. There we go. OK, a little more. OK, come on, Scratch. We'll fix this in post. Damn it. There we go. Oh, okay. Sorry, I need to fix this. There we go. OK, so pretend that never happened. But we probably don't want to have him turn only 15 degrees. We probably want him to reverse his direction entirely. So I think that's going to be 180 degrees. So let me go ahead and make that change. And then movement, he's going a little slow, but that's OK. So let me go ahead and drag him back to the middle of the screen, click our green flag, and really cross our fingers, as is not uncommon in programming. And come on. Come on. All right. All right, so still arguably a little buggy. I didn't really intend for him to go upside down, but he indeed literally did turn around 180 degrees. And there, too, that's kind of a key takeaway, is that in most any programming language, the language, and in turn the computer, are only going to do literally what you tell it to do. So if I simply told Scratch to sort of turn 180 degrees, that's exactly what he's going to do. He's not going to reorient himself as a reasonable human being might. We would have to write that code. Now, meanwhile, this gets very boring quickly. So how might I speed him up? Well, consider what it means to speed up. And consider, in fact, what animation really is, whether in comic book form, if you flip through the pages really fast, or if you watch a cartoon on TV or online. Animation really is just the process of showing me one thing after the other really quickly, typically. Now, this is not all that quick, but what if I told Scratch to take not just one step at a time, one small step at that, but like 10 steps at a time, or the equivalent of 10. I can't really move my feet that quickly, so we'll pretend. But I can tell Scratch to start moving not one step at a time, but, say, 10. And he immediately starts to bounce a little more animatedly. Now, we can have a little bit of fun with this, so a little bit of an intellectual aside. If we go to Scratch's sounds feature like this, let me go ahead and first stop Scratch here. Let me go ahead and click the microphone to record a new sound. Let me click the record button. Ouch! All right, so that is a waveform of what the word ouch looks like when I say it. I'm going to go ahead and delete the dead air up front and a little bit of the dead air here. I'm going to change the name to, let's call it ouch. And what's kind of fun now is if I go into sound, notice that ouch is among my available sounds. Now, when do I want to play ouch? It's kind of a condition too. Like only if I have walked into the stage do I want this to sound out. So let me go ahead and drag it in here. And now let's consider, before we get to the finale here, what's going on. When green flag clicked, do the following forever, again and again and again, move 10 steps. And that's what was getting Scratch to move pretty quickly. But then every time you take those 10 steps, take a moment to check if you're touching the edge, then turn around 180 degrees. But one more thing to do now, because again, both the blue and the purple block are inside of this yellow if branch. We're going to do both of those. So in theory, what Scratch is going to be doing is as he walks again and again and again and again and again, and he finally gets to the edge, hopefully he's going to turn around 180 degrees, but a little more literally than I, the human, might do. So let's try this. Oh, and actually, I left out one detail that Scratch will not. Ouch! 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 So ironic that the cat sounds more like me than I do when walking into walls. So that there is Scratch. It's just one programming language, and it's graphical at that. And we've only scratched the surface of its features. And indeed, there's more sophisticated things that we can do in order to program even more animatedly, even more sophisticatedly. And in fact, if we skim ahead to one of the first programs I wrote back in the day, let me go ahead and show you something called Oscar time. Sorry, we'll cut this part out. Here is Oscar time, and you'll hear in just a moment as I hit play, not only does this have animation, it's also got an incredibly long song, which, long story short, was not the best design decision back in the day, because as I worked through all of this program's bugs, all I heard was the Sesame Street song for, I think, 8 or more hours. But I have very fond memories nonetheless, and this then is Oscar time. So what's worth noting now? It looks very simple at first glance. We have some static imagery left, a trash can, what's in there, I wonder, and then a piece of trash that's fallen. But this is an opportunity to consider, how is that piece of trash fallen? Well, it's some kind of sprite, and indeed in Scratch you can have more than just a cat. You can have other animations on the screen as well. But what was happening with that piece of trash? Well, odds are I had it positioned originally at the top of the screen, and there's a puzzle piece that'll do that, and then I had it moving one or more steps at a time in a loop. But then here, instead of bouncing, which would be a little strange if your trash is just kind of bouncing off and up and down off the ground, I just have it stop. So there's probably a condition in there as well. I talked over another object that was falling, but there's another sprite, this blue sneaker, that also fell from the sky, but from a slightly different place. And it turns out in many programming languages, can you use randomness, or really pseudo-randomness, that the computer simulates. And so that's why the shoe, or the sneaker, actually fell from a different location. And if I kept playing this game again and again by restarting, odds are that trash, that sneaker, and now that newspaper would fall from different locations. So if you've ever played a computer game or a game on your phone, and it's not the same experience every time, like something kind of sort of changes, like the monsters start from a different direction, or the bad guy gets even harder or easier, depending on your level, that might be the result of some pseudo-randomness, asking the computer to just kind of pick a number, or pick a location, and then do something with that, so that the game is constantly changing. Now, this is not all that interesting if all I wrote was a program where trash is falling from the sky, but notice what you can do. You can grab things like the clock, click and drag, and notice this too is probably a condition. If near the trash can, open the lid, and again, here's the finale. Nope, here's the finale. As the trash falls into the can properly, does Oscar pop out and start counting? And indeed, if you do this again and again and again, it would seem that Oscar is using what? A variable? And indeed, that's how he's keeping track of a score, as might most any computer game. Now you can, well, head down. Now you can absolutely program games, animations, interactive pieces of art in a language like Scratch, and it actually indeed by design has a pretty high ceiling. You can write some pretty sophisticated programs, way more sophisticated and impressive than the one I did back in the day. But that's what's exciting about that, is that it's the result entirely of, again, this layering, using some very basic constructs, some simple ingredients, some building blocks, literally, whereby you build on these fundamentals of functions and loops and variables, conditions, Boolean expressions, and even more. And then so long as you take sort of baby steps, so to speak, biting off just a little piece of functionality, just get the trash to appear on the screen, then just get the trash to move on the screen, then get the trash to stop moving on the screen when it hits the ground, can you begin to take steps and steps and steps toward your final solution. But what's key in programming is to compartmentalize some of the features and to do them piecemeal, so that you don't just sit down with a blank window in front of you, try to bang out the whole entire thing, because invariably, if you're like me, the thing is going to be riddled with mistakes, otherwise known as bugs, because it's a little too hard to see everything clearly if you're not testing and testing and testing, perhaps along the way. But what do most people program in these days? Well, you can use Scratch, but generally speaking, someone's going to use a higher level, a more traditional language that tends to be textual and not graphical. So it's a wonderful environment to learn programming in. It's a wonderful environment to teach programming in. But you can very quickly take off these proverbial training wheels and start to use something a little more arcane, yes, but a little more powerful at the end of the day. And one of the earliest languages that was not binary and was not something called assembly language was this language here called C. Now this program too, quite simply, as you might guess, prints hello world. That's it. But there's a lot of overhead syntactically. I see weird curly braces and parentheses and a semicolon, \n. There's a lot of magical incantations here that would seem to suggest complexity. And yet all I want to do is just print out hello world. But C is representative of a type of language and a type of programming experience that's pretty representative of a lot of different languages as well. In fact, my computer, by default, doesn't understand this. Yes, it understands zeros and ones and some patterns thereof, thanks to the CPU. But it's not going to understand this, so to speak, unless I convert it, really, to zeros and ones. And so it turns out, when writing a computer program, I don't know how that happens. Oh, good point. Damn it, what was my sentence? Computer's not going to understand that. But the computer's not going to understand your, there we go. But the computer isn't going to understand this right from the get-go. We're going to have to first convert this language C, into those zeros and ones that the computer does understand. And the means by which we do this is typically as follows. I write in a language like C what we'll generally call source code. This is simply text like the lines you just saw a moment ago that ultimately just say hello world, but with some syntax around it to make that all happen. But the computer doesn't typically understand source code. It understands zeros and ones, otherwise known as machine code. So machine code is what the machine understands, and source code is what the source, me, understands. There's got to be something in the middle. And indeed, there's typically a program in the middle called a compiler whose purpose in life is to take source code as input and produce machine code as output. So before I can run a program like that, I have to run another program on my computer called a compiler. It might be called Clang, it might be called GCC, it might be called Visual Studio, it might be called Code Blocks. There's so many different compilers out there. But at the end of the day, what they fundamentally do is take one language as input and output another as output, and generally in a way that your operating system and your CPU both understand. Which is to say that writing and running a program is very often a two-step process. You write it, you compile it, and only then can you run it. It takes 2 steps up front or 3 steps in total. So not all languages, though, are like that. It turns out, one, there's languages that are syntactically much simpler. For instance, damn it. There's binary. Let me rewind if that's OK. How do I get to this point? Machine code. But what does this machine code look like? Well, it literally will look like zeros and ones. And indeed, if I run this source code through a compiler and don't run it, but look at it with a special program, I will actually see patterns of zeros and ones exactly like these. And even I, the human, in looking at this, don't really know what they represent. I could maybe convert it to ASCII, but that's not really going to get me anywhere. I would have to pull out my instruction manual from the Intel CPU inside my computer to actually understand most of these patterns of bits. So I'm not going to go to that extent. This is why we have higher level languages like C. But again, this isn't all that pleasurable to look at, to write. It requires a bit of cognitive overhead to remember all of this. There are simpler languages like this one here, Python, where thankfully you just say what you mean. Now there's still a little bit of syntax. There's some quotes. There's some parentheses. But at the end of the day, it's really far more so just the word print and just the sentence or phrase that I want to print. Gone are all those curly braces, the requisite semicolon, and more. And so certain languages are a little simpler. And indeed, Python and other languages are the result of programmers and humans more generally having learned, gee, wouldn't it be nice if this were a little simpler? Wouldn't it be nice if this language did a little more of this work for me, made certain assumptions for me, so that you don't have to write and remember as much complexity as we saw a moment ago. But Python's an interesting one, too, because it is generally interpreted, so to speak. And that's a bit of an oversimplification. But when writing code in a language like Python, we again still have source code, just as we saw a moment ago, print hello world. But you don't convert it to machine code per se, at least not explicitly. Rather, you run it as input into a program called an interpreter, whose purpose in life is to do exactly that, to interpret the lines of code that you've written, top to bottom, left to right, and actually translate them essentially into the language that the computer can understand. And it does this, though, not by converting them to zeros and ones, but by outputting something called bytecode, which is an intermediate representation of the language. So it's much more cryptic, as we'll see in just a moment, but it's not as cryptic as zeros and ones. And so when you use a language like Python and others like it, you will often install a special piece of software, whether you realize it or not, called a virtual machine, or VM. And that virtual machine is kind of like an imaginary CPU that can work on Macs and PCs and other computers still, that someone out there has written that understands bytecode, and the virtual machine in turn is what is running at the end of the day. And it's running your bytecode, which is the result of your source code. And long story short, even though this looks like a more complicated process, what's nice about this process in many of these newer languages is that a lot of these intermediate steps are completely hidden from you. If you want to write a program in Python, you simply write it as source code, and then you run a command at your keyboard, and that's it. There's no explicit compilation process that you have to worry about as the programmer. The computer might be doing that for you underneath the hood, and indeed it is, but it's been abstracted away, so to speak. So let's see these two examples in action and realize the result of this process in Python is going to look. Now let's see. Now let's see these two examples in action. But first, the intermediate language that Python is going to generate in order to be run on its virtual machine is this bytecode here, something that looks a little bit like this. You can kind of sort of figure out what's going on. I see print, I see hello world, but there's some other stuff that I don't necessarily understand at first glance, but that's OK, because the virtual machine that's going to run this ultimately will. So let's see this in action. I'm going to go ahead. Set. So let's see this in action. I've gone ahead and opened up a terminal window, so to speak, really a black and white window on my Mac, or a PC for that matter, that has some software pre-installed, software that does understand C and Python and even some other languages as well. I'm going to go ahead and open a program called Nano, which is just a simple text editor, and I'm going to open a file called hello.c. And not to worry about what some of the syntax on the screen here is, what's important is that I'm going to retype the same thing we saw a moment ago, include standard IO, int main void, and then in here, I'm going to do printf hello world, \n, close quote, close parenthesis, semicolon. So I have just recreated that program in C, and I'm going to go ahead and save it in a file called hello.c. So all I've done is open the textual equivalent of Microsoft Word, but a super light and friendly, well, less friendly version perhaps of it, but that I've used many times before. I'm now going to go ahead and type the following: clang for C language, -o hello, space hello.c. So again, another one of these sort of magical incantations that I understand because I've done it before, but you could read this in a manual or be taught this in a class. And what this is telling my Mac to do is to compile hello.c into a new file called hello, inside of which are those zeros and ones. If I go ahead and hit enter, nothing appears to have happened. But if I now type this command, /hello, where dot just means go into my current folder, and hello means run the program called hello, we shall see if I did this right. Hello world. Underwhelming result, but a correct result. But it did take a few lines of code and a bit of complexity. If I instead run nano of hello.py, where pi is commonly the extension for a Python program, and instead I literally just type print hello world, and then, and then save this file, and now run Python hello.py and hit enter, you'll see the exact same result with arguably a decent amount less effort. So these are just two languages now. There are so many other. Now, these are just two languages now. There are so many others out there. For instance, here we have an example of this same program, fundamentally hello world, in a language called C++, which essentially adapts C and adds some new features to it while changing a few things as well. And you can see the syntax alone is already a little bit different by convention. Here's an example of hello world in Java, a very popular language, formerly in the context of little things called applets on the web, but more recently in enterprise software on the back end for servers as well, is commonly used as a teaching language with students in school. This here is an example of a language called Ruby, which is often popular at the command line in that black and white environment where you're running commands with your keyboard, as well as in the web context using a framework called Rails, or Ruby on Rails, if you've heard of that. Lastly, here is another example, this one in a functional language called Lisp, whereby you tend to have more parentheses, and it's what's an example of a functional language, which doesn't just mean that it functions. It's a fundamentally different type of language than the others we've looked at thus far, which are procedural or imperative, which is only to say it's a somewhat different mental model when it comes to programming in languages like this, but you can still print out things like hello world quite simply. And then there's JavaScript, which exists in a number of contexts today, both in the context of the web browsers, but also in web servers. This is how you might, on the server side, print out something like hello world. But JavaScript is an interesting one, too, because there's newer and newer features of the language itself. And this is true of a lot of languages. They evolve over time. So humans don't just invent new languages. They sometimes go back and improve on and increase the version number of past languages by updating the tools that understand them. So Clang, like I ran a moment ago, which was my compiler, and Python, which I ran a moment ago, which was my interpreter, and coincidentally also the name of the language, those can continually be updated. You can download and upgrade versions of those, and they'll support newer versions of the language. And so it's very common these days for JavaScript to actually be newer than is actually supported by browsers out there. And so a common term of art in this world now is to transpile, not compile, but transpile JavaScript to JavaScript, specifically from a newer version of JavaScript to an older version of JavaScript, maybe like English to Old English, simply because the browsers of today don't necessarily understand the newest version of English. They're still speaking something from yesteryear. So there's any number of methodologies, there's any number of languages you might use, and indeed this is just a few of them here. You might recognize some of these names here. Many of these are increasingly used in the web, in the web context, to actually build websites, to build mobile applications, to build things that are optimized for your phones. But the ... suggests we're really just scratching the surface. And if you've ever wondered what more there is, let me invite you to go to Wikipedia or beyond, and you'll see an overwhelming list of languages and also a lot more of the history of these and many other languages. But of course, the examples we've done thus far have been in the graphical context like Scratch. They've been in the textual context like C and Python. What we haven't done is actually leverage the World Wide Web. We've not actually written a program that runs on my phone, it would seem. We've not yet written a program that runs in my web browser, on my laptop or desktop. To get to that point, we're going to need a few more ingredients, a few more building blocks, if you will. Languages like HTML, not a programming language, a markup language, but it's the language in which web pages are written, and it provides us with a new and improved context, perhaps, for writing software using the same ideas, but with different user interfaces on the phone. But to get to that point, we're going to need to understand a little bit about that other language, HTML. We're going to need to understand a little bit about the World Wide Web. And ultimately, we're going to need to understand how the internet itself works. All right. That was much better than Tuesday, if I may say so. OK, yes, those of you who are actually still tuning in online, we're going to now change pace and shoot a different lecture for CS50 for MBAs, picking up exactly where we just left off. We're going to take a few minutes here to recuperate. We're going to do a little wardrobe change, and then we'll be back in just a moment. What are we streaming now? Just video or audio too? Sure. Okay, hello world. We'll be right with you. Where's my files? All right. All right. All right, hello world. We're about to be back with CS50 for MBAs. This is just a live stream of our shooting of CS50 for MBAs behind the scenes. We again have CS50's own Scully, this time doing the live cut. CS50's own Ian Sexton here on camera 1. Dan Coffey's now up front on camera 3, and Arturo here on camera 2. Our subject today is the internet. All right, ready when you are? Okay. Very professional. So I'll start over here again, I think.
You want to start on AJ and then go to
Sure.
one again? Here we go. Stand by. 5, 4, 3.
So odds are you're on the internet these days. But what does that actually mean? And indeed, this internet that we use very often these days for messaging, for email, for browsing the web, and other services still, there's a whole infrastructure that underlies it that is increasingly powering new ideas, new startups, new companies, new businesses, as well as new forms of communication among humans. And yet, like most every topic we've explored, you'll realize that while it's very complex perhaps up here, or certainly seems complex up here, if we begin with some of the fundamentals and then layer and layer and layer on top of those, do we pretty quickly get back to today's technology, but with a much better understanding of what's going on from the ground up. So here is a bit of alphabet soup. Odds are you might have seen one or more of these acronyms to date: IP, DHCP, DNS, TCP, UDP, ICMP, and so many more. These are all examples of something called protocols, where protocols are kind of like languages that computers speak with one another. They're not programming languages, so they're not used by humans to make computers do things or follow instructions per se. A protocol is really a set of conventions that two computers or two computer programs might use when intercommunicating. And so what's an example of a protocol in the real world? Well, we humans have some silly protocols, one of which here is culturally when you meet someone to extend your hand, and then he or she presumably extends their hand, and you do this for who knows what reason. And now you've sort of completed that social transaction. But it's a protocol in the sense that when I extend my hand, most any polite other person knows that they're probably supposed to extend their hand as well, embrace for a moment, and then complete. And the protocol says, too, you probably shouldn't do this for terribly long. And so there's these rules of thumb, or actual rules that you follow when implementing protocols. And so computers, great as they are at following rules, very often use protocols when they intercommunicate in order to get data from one place to another. So let's tell exactly that story. If you're on the internet, indeed right now on the internet, what does that actually mean, and how can it help us solve problems ultimately, having access to this inter-networked infrastructure? Well, let's consider what happens when I first visit my favorite web page, for instance. If I go ahead and visit something like Facebook.com, I go ahead and log in, and I'm immediately presented with my news feed. Or maybe your favorite website is Gmail, or your favorite website is Bing, or maybe your favorite website is any number of other places you might go on the web, all of which take in as input a request from you and produce ultimately output. the screen that you ultimately see. But how does that data get from one location to another? Let's begin to draw a picture, perhaps. And this picture might be representative of your own home network, or maybe your campus network, or maybe your office network. But generally speaking, you are on the internet, maybe with your phone or your laptop or your desktop device. And we'll just depict that as this sort of abstract laptop here. So that laptop somehow wants to communicate with a web server elsewhere, Facebook, Google, Bing, whatever. And we're just going to present that as way over here in the picture in a really big corporate office building, perhaps. And inside of that building are the servers that compose that particular website. But how do I get data from that server, which if it's Google or somewhere else might be all the way in California or halfway across the world, and back to my laptop? Well, somehow I have to be able to send messages to it and receive messages from it. And of course, in between me and this resulting website is what we'll generally call the internet. It's kind of conveniently drawn as a cloud here, which is another semi-technical term that's come into vogue in recent years. And the cloud really just refers to internet services these days. It's not a technical term unto itself. It's just a sexier term than saying, my business is on the internet. Oversimplification, and we'll come back to that before long, but you can assume near that the internet is somehow this delivery mechanism. It somehow gets data from point A to point B and back. But how does that work? If my data is coming in as input and it's reaching eventually its destination, and then a response is coming back in this direction, what's actually going on underneath the hood there? Especially since, in the story at hand, all I've typed is something like facebook.com or gmail.com or the like. Well, it turns out that your computer these days, when you first turn it on and you connect to like the Wi-Fi or in a room, or you connect with an Ethernet cable to the wired network, your computer receives some information automatically. Your computer speaks a protocol called DHCP typically, Dynamic Host Configuration Protocol. But in most of these cases, the acronym isn't really what's important, certainly. It's what the protocol itself does. And in this case, this Dynamic Host Configuration Protocol dynamically configures hosts via a protocol, if you will. So what does this mean? Essentially, DHCP says this. When you turn on your computer or you take out your phone for the first time and you're connected on Wi-Fi or to a wired network, it says, hello, world. I am alive. I would like to be given an address so that I can communicate with other computers on the internet. It's not quite that verbose, perhaps, but it is a question. Hey, computers around me, please give me an address. And what it gives you is what's called an IP address, Internet Protocol. So just as in the real world, where physical buildings have historically been uniquely addressed with postal addresses, like Harvard's computer science building is at 33 Oxford Street, Cambridge, Massachusetts, USA. 02138 is the more precise zip code as well. That uniquely identifies that building in the world. So does my computer need an address. And it's not going to be some free-form address like that in words. It's actually going to be a numeric address. Specifically, I'm going to get an IP address of the form number.number.number.number. So 4 numbers separated by dots. Each of those 4 numbers happens to be a byte long, or 8 bits. So each of these numbers, therefore, is between 0 and 255. And so this means, long story short, that the total address is 32 bits, 8 plus 8 plus 8 plus 8. And that means there's 4 billion possible addresses in the world. And that's great, because people got a lot of computers and a lot of laptops and a lot of desktops and servers these days. But it turns out we're actually running out because we have so many such devices. So there's a newer version of IP that's increasingly being used called IP version 6. We're talking here about IP version 4 since it's so omnipresent. And IP version 6, just so you know, uses 128 bits for its addresses, way more than 32. So we'll be good to go for some time. But DHCP gives me this address, an IP address of the form something.something.something.something. And the purpose of this address is to help my data get from point A to point B. And indeed, anytime my computer sends a request out on the internet, like Facebook, please show me my newsfeed, or Gmail, please show me my inbox, my computer has to use that IP address. So much like if sending a letter in the real world, you might have an otherwise blank envelope, and you might want to send a message to someone else in the world. You might write their physical address, but in the computer world, we might write something like 1.2.3.4 in the to field, assuming that this is the IP address to which we want to send this data. Meanwhile, my from address might be 5.6.7.8, so I'll write it in the top left-hand corner by convention, whereby that indicates to the whole internet, this is where this request came from. Now, I know my origin address, the source address here at top left, because DHCP told me. How do I know 1, 2, 3, 4? How do I know the IP address of Facebook.com or Gmail.com, right? We don't live in the world of 800 numbers anymore where you dial 1-800 something, 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 and you have to advertise your phone number per se. We don't necessarily live only in the world of 1-800 collect anymore, where we had these mnemonics where you had letters mapping to numbers just to help remember it. We went full in on this idea of mnemonics such that now we have Facebook.com and Gmail.com, and no numbers whatsoever for us humans to remember. So thankfully, turns out there's another system in this world, another acronym, if you will, a new one now, called DNS, Domain Name System. So there are also in the world not just DHCP servers that hand people IP addresses from their local network. There's also DNS servers whose purpose in life is to convert domain names to IP addresses and vice versa, and a few other features as well. Now, what does that mean? That means that when my Mac or my PC sees little old me, the human, typing facebook.com or gmail.com, my laptop contacts a nearby DNS server and says, hey, my human has asked me for facebook.com. What is its IP address? And a DNS server's purpose in life is to answer that question and say, oh, facebook.com, it's 1.2.3.4. Use that address instead. Now, thankfully, my computer can now write that number on its virtual envelope, so to speak, and then pass that envelope out to the internet. And because of these numeric addresses, it will be properly, hopefully, routed across the internet to its destination. Because it turns out inside of the internet here, interconnecting everything in between point A and B are things called routers, or gateways. And I could draw this picture in any number of ways, but the point is that it's just so darn interconnected. And indeed, there might be even more pathways still, or maybe even fewer pathways. Indeed, on the internet, there's often multiple ways for data to get from one point to another, some shorter, some longer. But there's this resilience, this redundancy. And this was a feature back in the day, especially insofar as the internet had militaristic origins. It was meant to be redundant so as to withstand failures of one or more of these nodes, these dots in the picture. Now, each of these dots is just a server, really, a special server called a router or gateway, whose purpose in life is to do exactly that, to route data. Upon receiving a virtual envelope like that one, it looks at the to address, realizes, ooh, this is destined for 1.2.3.4. I know that that address is over this way. Meanwhile, if it gets another envelope from someone else, it might say, ooh, this is some other address. It's going to go this way. And so routers have multiple cables, or they have multiple virtual network connections elsewhere, or wireless connections. Any number of possible connections might they have to other routers. And so it can route it to its next hop, so to speak. And generally on the internet, within 30 hops, within 30 transmissions from router, 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 will your data get from one point to another. And it might not follow the same path each time, but it will traverse this so-called internet. And so that's kind of what the internet is. It's this collection of routers, and it's this collection of networks, a network of networks that is incredibly interconnected in different ways. So DHCP gives me an IP address, so I have a unique IP address. DHCP, turns out, also tells me what the IP address is of my local DNS server, so I know whom to ask to convert domain names to IP addresses. But once I have that, I can now use a protocol called TCP to send my data reliably, typically from one point to another. So whereas IP is responsible for a few things, one of its most important functions is this notion of addressing and standardizing how things are addressed. But TCP, one of its most salient features is to guarantee, with high probability, delivery. And what I mean by that is that bad stuff can happen in the middle of the internet. These routers can get really busy. They can get really congested and overloaded. And so routers might virtually drop packets. They might receive so many packets at once, they just can't, like a human, deal with it all at one time because they have a finite amount of memory or RAM or disk space. And so they drop them, so to speak. They just delete them, and they expect the senders to resend them. TCP is a protocol, another agreement between computers, that if the receiving computer realizes, I got some of your packets, but not all of them, TCP mandates, much like our human handshake, that something next should happen. TCP says my laptop should retransmit that virtual envelope. And so hopefully all of them are ultimately received at the end. But there's other ways. There's other protocols for point A and point B to get data from one to the other. There's something called UDP, which is common in some circles as well. UDP works a little differently insofar as its feature is to not guarantee delivery. If some data gets lost, packets get dropped, so to speak, for whatever reasons, malfunction, technical difficulties, routers are overloaded, UDP says, our protocol shall be not to retransmit that data. And that's a strange thing, because it sounds worse, and yet this protocol has been around for quite some time, still used, quite appropriate in some contexts. But what context would you actually want to just forge ahead, irrespective of getting complete information? Well, go-to here is something like video conferencing or audio conferencing or live TV on the internet, watching a game, like a football game, for instance. If you want to watch it in real time, you might prefer that the stream, the bits that are coming from the NFL or wherever to your computer, don't actually buffer, don't actually stall. You would rather miss a second so that at least you stay current in real time with that game. Or video conferencing, even more so. It's kind of annoying if you have a bad connection or some packets get dropped and you just have to wait and wait for the person's voice or image to be retransmitted. You'd rather just say, what did you say? Could you repeat yourself? Say again. You can just use human protocols to deal with that too. So sometimes you want live streaming applications for whatever purpose, and you want the data just to keep coming. As much of it as can make it through is great, but you don't necessarily want it to be resent. So data is going from one point to another, but how long does all this take? My God, this is kind of a long story just to get data there. Well, let's do an experiment. Let's go ahead and pull up a program that uses a different protocol altogether, ICMP, and there's other protocols still. This one's a little more technical, but it's wonderfully revealing in a few ways. I'm going to go ahead and open up a so-called terminal window, a black and white window on my Mac or my PC or other types of computers as well, that has a bunch of commands built in. And one of the commands is called traceroute. And it's going to literally let me trace the route of data from my computer or the server I'm connected to some destination. So I'm going to go ahead and run this. Trace route to, we're here in Cambridge, Massachusetts, on the east coast of the United States. Let's go ahead and see the route from us to our friends at Stanford University in Palo Alto on the west coast of the US. Hit enter. Oh my God, that is just not comprehensible. And indeed, there's a lot going on there, which is not as expected, sorry. OK. Say again? Oh, it's flickering, right? Yeah, if we can ideally avoid resetting it, that would be ideal. I tried to avoid standing too close to it.
Did that just flicker? I did. I'm just trying to see if this one is flickering too, to figure out where the problem is.
OK. Just thinking. OK, ready when you are. Let's actually trace the route. OK, ready? OK. So let's use another protocol, this one a little more technical. Oh, sorry. Actually, trace the route. So let's try another protocol, this one a little more arcane, called ICMP, and others that are going to allow us to trace the route from one computer to another, indeed using a program called trace route. I'm on my Mac here in a so-called terminal window, though you can pull up something similar on Windows and other operating systems as well. And what I'm going to do is literally trace the route between my laptop here and some foreign server, for instance, one on the west coast of the US, Berkeley's web server. So let me do that. Trace route, www.berkeley.edu, enter. And curiously, we start to see a whole bunch of lines of output, most of them numerical. And indeed, notice that each of these is an IP address. But what is it an IP address of? Well, we have like 18 of these between me and Berkeley, apparently. Turns out those represent routers between me and Berkeley, California. Each of them has an IP address, and each of them has a measurement of how long it took my data to get from my Mac to that router. It's highly variable. Notice it's kind of all over the place. In fact, this is just weird. This took like 3,000 milliseconds or 3 seconds. So I'm guessing that that router in row 8 was congested for some reason, some kind of network issue there temporarily, but then my data actually went through. And it's not cumulative. These are individual tests from my Mac to each of these routers iteratively, one at a time. And you can kind of get an aggregate sense of how long it takes, therefore, for data to get from the East Coast to the West Coast. If we look at some of the later numbers, they're kind of variable, but they seem to be around 75 milliseconds. So this is kind of extraordinary. If you want to fly from Boston, Massachusetts to like San Francisco, it's going to take you 5, 6, 7 hours. You want to send an email or send a packet, it's going to take you 75 milliseconds. Like, that's astonishing how quickly the data can transmit. Now notice this is not all that enlightening knowing these IP addresses, but eventually some of them have domain names. Just because the humans controlling those routers decided we are going to give these routers actual names, domain names, as opposed to just having IP addresses. And you can often, but not always, infer from the domain names where they are. So I'm going to guess that at least row 11 here, I don't know what xe7000.rtsw is, but LOSA.net, Los Angeles in California. I'm guessing my data kind of came into Southern California first, but then notice what happens next. A couple nameless servers, LAX. So maybe that's the airport. Indeed, routers, for historical reasons, tend to be named after nearby airport codes. I'm not sure what this next one is here, but I do recognize Oakland and UC Berkeley. So I'm guessing one of the next routers is actually in Oakland or near Oakland. And so that's a pretty long cable or interconnection essentially between LA and Berkeley. But the result ultimately is that my data makes its way to Berkeley, this time via this path. If I ran it again now or in a day or a week, the path might be a little different based on congestion and interconnectivity. But the data actually gets there. And cutely enough, it looks like Berkeley's web server is called CalWeb Farm, prod for production, ist.berkeley.edu. 75 milliseconds only. But what about this? What if we don't stop at the edge as we do at the edge of this continent, but keep going? What's going to happen? Well, let me try to trace the route to, say, www.cnn.co.jp, the domain name for what I presume is going to be the Japanese version of CNN's website in Japan. Here, too, we have a bunch of nameless servers just with IP addresses. Gets through them pretty quickly. We seem to have some lulls. Sometimes this program sometimes the routers won't respond to these queries, so they remain essentially anonymous. But now this is quite interesting. Oh, my God. We went from routers 12, 13, 14, 15, taking about 63 milliseconds, give or take, to 193 milliseconds, which isn't a blip because it stays around that value, 180 milliseconds, 160 milliseconds, 177 milliseconds. That's a big jump of 100-some milliseconds just between routers 15 and 16. Why might that be? What could be between routers 15 and 16? Well, if you know your geography, it might very well be the Pacific Ocean. There's quite a bit of distance. There's quite a bit of cabling that actually connects the west coast of the country to Japan and other areas in Asia and beyond. And that's what's pretty amazing. Not only is there interconnectivity on the internet these days via cabling and via Wi-Fi signals and via satellite signals, via microwave signals and the like, you have so many different ways for data to be transmitted. And it's absolutely astonishing and exciting, dare say, just how interconnected the world now is. In fact, thanks to this animation online, let's take a look and appreciate just how extensive this network actually is. All right, so let's actually solve a problem now with this internet. Right? The internet, as you've probably heard, is filled with cats. And yet these cat images can be pretty big. And indeed, bigger still than images are things like video files from Netflix and the like. And so there's huge amounts of traffic transmitting over those kinds of interconnections. So how do we ensure, at least with high probability, that data can actually get through? How can we ensure that there's some form of fairness, if not net neutrality, so that my data can get just to its destination just as readily as your data can get there? Well, sometimes it's opportune to actually take big packets of information and chop them up. So indeed, what a computer will often do, thanks to TCP/IP, the combination of these protocols, is we'll take large files and large images in this case, tear them off into, say, roughly equal-sized parts, like this here, and then tear it down even further, perhaps, to get it into a smaller bite-sized piece, and then send not only one packet of information over the internet, but instead put one piece of information in this packet here, put one other piece of information in this packet here, whose addressing, both to and from, is identical, and then do the same thing for the two other pieces, so that ultimately we have 4 packets, each of which contains one portion, 1/4 in this case, of the resulting message, all of which are destined for the same destination. But the problem to be solved now is, what do you do with this information? If I have 4 seemingly identical envelopes, but inside of which are disparate pieces of information that somehow need to be reassembled, let's put on our proverbial engineering hats. How do you solve this problem? Is this sufficient information on the envelope so that if I send this out on the internet toward Berkeley or Stanford or Facebook or wherever, how does that recipient know what to do with it? Like, what would you, the human, do if you have not virtual but physical envelopes? Well, here too. And here's an opportunity really to bring to bear human intuition to a problem that seems fairly technical and well beyond one's own technical understanding, and yet it really is just a technical manifestation of a real world problem. I need to keep these in order somehow. So you know what? I'm going to say something like 1 of 4 on the first one, like this. The next one I'm going to say 2 of 4 on the next one, like this. And then I'm going to say 3 of 4, and then on the next one here, I'm going to put 4 of 4. And what's the takeaway now? Now, whoever is the recipient of these several envelopes as I send them out on the internet, and indeed, they don't have to follow the same path. One can go this way. One can be routed that way. Another can go to this router. Another can go to that router. Because they're all addressed, and because all of these routers are somehow interconnected, all 4 of those packets will hopefully get to their destination. But if they don't, the recipient can look at that additional detail I wrote on the envelope and see, ooh, I got part 1, I got part 2, I got part 3, but where is part 4 of 4? It didn't arrive because of congestion. Literally got dropped on the floor and not picked up. And so the computer who's supposed to be receiving that data, thanks to TCP recall, can say, hey, please send me, again, packet 4 of 4. And so as technical as the internet might seem, it really, again, is just some fairly intuitive solutions to problems like this, albeit translated to more technical contexts, more technical protocols, and more technical languages. But let's look at some more user-facing protocols. The ones we've discussed thus far are fairly low level, if you will. And indeed, there's this whole internet hierarchy of protocols, layer on protocols, layer on protocols, so that what we humans really tend to care about, if we're not the engineers, but we're really the software developers and we're the users of applications, we care about application layer protocols that is right between the human and all of those lower level protocols. For instance, these, at least one of which has got to jump out at you, HTTP. Odds are you've seen this. Odds are you've typed this, though decreasingly you have to still type it because browsers will just add it for you. HTTP, the secure or encrypted version, HTTPS, IMAP for email, inbound, SMTP for email outbound, SFTP for secure file transfer, SSH for secure shell, an encrypted textual channel between two computers, and many more. But HTTP, let's focus on that one because that is Hypertext Transfer Protocol. Or HTTPS, the same, but the S stands for, not savings, secure. Secure. So it's actually encrypted in this case. So what does this actually mean? Well, at the end of the day, HTTP is a protocol that governs what kinds of messages go inside of those envelopes that I've been preparing for the internet. What kinds of messages go inside of those envelopes. And it turns out the simplest message that a computer sends through this whole internet ultimately, inside of that virtual envelope is quite often, thanks to HTTP, a message inside of which is a command like this, get me slash, where slash is the default root or name for the default file on a web server. And the envelope might also contain, oh, by the way, let's please speak the latest version of HTTP 1.1 as opposed to an older one, 1.0. But that's it. Inside of that virtual envelope, if it's not a cat, which is a response from a server perhaps, it's a request for a cat, something like this. So this request line might say, hey, please give me a cat. Can we rewind and redo this part? Sorry. So if HTTP is the protocol that governs what goes inside this envelope, let's take a look inside one envelope that leads to that cat actually being transmitted. Inside of this virtual envelope, if I'm trying to request a cat from the internet, might literally be a message like this. Get me, for instance, slash cat.jpg for JPEG. And maybe some additional text after that, maybe some additional text below that. But at the end of the day, inside the virtual envelope, if I am on the internet and I'm going on Google Images and I want to find a picture of a cat, inside of my envelope, if I am a web browser, speaking HTTP, is going to literally be a textual message that says get/cat.jpg, if I know that's where the image is on some server. The response is going to be what was just inside of those 4 envelopes back from the server to me, chopped up maybe into multiple pieces, but in a way where I can then realize, oh, wait a minute, you sent me only 3 of 4. Please resend me the 4th one. So it works in both ways, whether it's me sending a cat to someone or receiving a cat from someone. This protocol, HTTP, governs how the messages are formatted and what language, so to speak, is spoken between web browser and server. So indeed, HTTP is entirely about having a web browser communicate with a server. And we can see this. Let me go ahead and pull up Google Chrome, a web browser that you yourself might use. Subtle. Thank you. Stand by. Stand by. OK. So here I am at Google Images, and I want to search for a cat and download a cat. Well, let's, oh, this is going to be misleading. Nope, let's do a different example. OK, no, we're almost done. OK, we'll go to Facebook, I think. I don't want to go to Google. Damn it. OK. So I've pulled up Google Chrome now, and my goal at hand is to search for cats. Let's be a little more productive. Let's go on Facebook. But I want to see what traffic my browser is actually sending to the server. So it turns out that if you control-click or left-click on Chrome, on the background there, you'll typically see this contextual menu, and you'll often see a menu option like this, Inspect. And Firefox and Safari and Edge have similar options as well. And if you click on Inspect, you'll see, oh, shit. OK, no, we're not going to do that. OK, how do I get to this point? So let's now actually pretend to be a browser. I'm going to go ahead again and open the so-called terminal window, this textual interface via which I can actually interact with my computer. But this time, rather than trace the route between point A and point B, I'm going to go one step further and actually pretend to be a server. Sorry. So let's actually see this in action. Now I'm going to go ahead and pull up a, oops, sorry. Now I got it. So let's actually now see this in action. I'm going to go ahead and pull up a so-called terminal window again, this textual command prompt on my computer, and I'm going to pretend to be a browser. So I'm not going to just trace the route between point A and point B. I'm actually going to request a web page as though I am Chrome or Edge or Firefox or Safari or whatever your favorite browser is. But of course, as before, all I know is that I want to visit my favorite website, facebook.com, for instance. But I don't know its IP address necessarily, so let's go through that step. How do I look up its IP address? Well, my Mac already has an IP address because of DHCP. I'm already powered up. I'm already connected to the Wi-Fi here on campus, and so I already have my own IP address. And I also have the IP address of a DNS server, so my Mac just knows that. But I can use that capability now to look up the name, the IP address for the name Facebook. And I'm going to do that as follows: NS lookup for name server lookup. And I'm going to go ahead and type in www.facebook.com, enter. And interestingly, we get back this somewhat cryptic response, but let's make some sense of it. So it looks like the server that this response came back from is 10.0.0.2, which happens to be a private IP address here on campus that you might have in your own company or university or even home network. Then a non-authoritative answer is this: www.facebook.com, whose canonical name is, curiously, star-mini.c10r.facebook.com. Well, it turns out that companies like Facebook absolutely have many, many, many different web servers. And they might not necessarily have just one IP address, but we might just be seeing one IP address depending on where I am in the world and depending on how Facebook has configured its infrastructure. The takeaway then is that apparently, so far as my Mac is concerned, www.facebook.com is an alias for, or a synonym for, this longer, less well-marketed domain name here. But what we really care about, if I'm about to pretend to be a browser, is this IP address. Facebook's IP address is apparently 31.13.65.36. And I can see this, in fact. Let me go into Google Chrome, or any browser for that matter, and go to http://31.13.65.36, enter, and voila, I made it to Facebook. Now, of course, no one in their right mind is going to advertise the IP address as 31.13.65.36. No one would remember that. We're not in the age of phone numbers on the side of billboards anymore. Now we have domain name system and DNS, which does this conversion for us. But now that I know that IP address, I can use this information and pretend to be a browser and not just see the response in Chrome as we just did, but I can see it in my textual window, so I can look inside the envelope. Indeed, this terminal window is going to let me pretend to send, well, actually send a message as though I'm a browser, pretending to be one, but it's going to let me see inside of the response that comes back. Here's what I'm going to do. I'm going to go ahead and type in curl curl-i, and I'm going to go ahead and type http:// and then that IP address. And I'm going to hit enter. And notice, uh-oh, Facebook has moved permanently. But this is a good thing. To where has Facebook moved? Well, apparently, we've gotten back a response via version 1.1 of via version 1.1 of HTTP that Facebook, per this status code, so to speak, has moved permanently. Has moved permanently, which sounds scary, but where has it moved to? Oh, they don't want people visiting their IP address, even though it works. They want to redirect people, so to speak, to their domain name. So we seem to be kind of in a cyclical situation here where, wait a minute, I thought I had to convert my domain name to an IP address. And indeed I do, but it turns out curl is pretending to be a text-based browser here effectively. And it is already going to do this DNS lookup for me. So this is OK. I'm going to go ahead now and do curl http curl-i http:// sorry. I'm going to go ahead and do curl-i http:// I'm going to go ahead and do curl-i http:// www.facebook.com, enter. Oh my God, Facebook moved again. But where did they move this time? Well, it seems that Facebook would prefer that we visit https:// which is the secure, the encrypted version. OK, I can oblige. Let's go ahead and do that. Curl-i of the HTTPS version, which I've just pasted in, enter, and voila. Now, this looks overwhelming. But what's really important is this message here. It turns out everything is OK. And indeed, what's come back from the server is a virtual envelope, inside of which is this message here saying, hey, no big deal, everything is OK. And you never see this number when you visit web pages, unless you're a software developer and you know what tools to use. Instead, some of us out there, some of us normal humans, occasionally see a different number. It's maybe the one number you associate with the web. Let me simulate it as follows. Let me go ahead and request this completely bogus page. Hopefully that's not actually someone's username. And hit enter, scroll back up a bit. What do you notice this time? If you've ever wondered what 404 means, it is the numeric code inside of a virtual envelope coming back from a server when you have requested some nonsensical URL because of a typographical error or just nonsense that I typed that's now having the server tell you, not found. 404. So this is just a special numeric code. And this is common in programming to have numbers correspond to different types of things that can go wrong, or better yet, that can go well, as in the case of 200 OK. Now, all of this stuff is called HTTP headers. So I was oversimplifying earlier when I said HTTP is just this handshake of sorts between servers where you say, get me a cat picture, and then you get back the response as per those 4 envelopes. There's more headers. There's more key value pairs, words with colons, words with colons, words with colons, and then values to the right of those. And that is just additional metadata, more information from the server that tells you a little something about it. But if I instead run that same command one final time, this time doing curl, and then specifying not -i, but just the URL itself, and hit enter, this craziness comes back. And this looks like a whole lot of programming language in something called JavaScript, or big JSON object. And my God, look how much data came back from the server. But notice I'm starting to see some structure. Open bracket div, and the word label here. And if I go up here, input here. And indeed, what you are seeing is a language called HTML. Inside of the virtual envelope, if you're requesting not a cat image, but a web page that has your news feed or your inbox from Gmail or your search results from Google, is a language called HTML. And HTML is not a programming language. And indeed, it's not as cryptic looking as this. Google is being or Facebook is being very efficient when it comes to showing me this information and just getting rid of as much formatting as they can to save space, to save on internet bandwidth, the transmission thereof. But it's a language that comes back in this virtual envelope that a browser knows how to display. It's a markup language in the sense that it's going to tell the browser what to show on the screen, where to show the cat, where to put words, whether to make those words big or bold or italics or centered or any number of other things. And indeed, what you are seeing is this. This is www.facebook.com graphically as we see it in the browser. Underneath the hood is that black and white, seemingly nonsensical Greek, if you will, that at first glance, there's no way most of us would understand it. But that's because we're looking at it here. We need to dive in a little deeper, take a look at what HTML is, how it's actually structured, make the simplest of web pages, a hello world of web pages, if you will. And then can we realize and build back up to this point exactly what composes pages like Facebook and Gmail and Google and Bing and others. Because at that point, we'll have understood not only how the internet works, but how you can use it as a delivery vehicle for your ideas, for your programs, for your products, for your companies and more, and actually deliver information and deliver cats and much more to your users on this internet. I think so. It didn't flow as much as the first one, but I think we hit the points I want to set up the next thing. Yeah. Oh. Is that to cover up all the mistakes I made?
No, so we can get the still image for this lecture.
Oh, nice. OK. Yes, I shall. What is it, 587? OK, we're going to have to cheat this. OK. OK, so for the editing later, if it's possible to weave this in, context here is we were going through these lower level protocols. We talked about TCP as being the protocol that guaranteed with high probability transmission. Wanted to make one mention now of the port numbers that it uses to identify services. Let's see, how best to do. I have no idea where best to stand for this one. What's, we'll do it over here. Let's see if this works. Here, essentially, when did I throw the package? Was this still on the screen? Do you remember? This was after I did that? All right, let me try something. Let me stand in no man's land where we at least have a shot here so that we can maximize probability of this being useful. Yeah, and maybe hide my hands because I'll bring it up. OK. But TCP does something more than just guarantee with high probability delivery. It also allows us to send different types of data to the same server, even if it's, But TCP allows us to do something more than guarantee with high probability delivery of data. It also allows us to multiplex among services. Or put more simply, it allows a server to receive different types of data for different types of services. For instance, web services on the server, email services, chat services, and the like. And so it turns out that on this virtual envelope that gets sent from a computer to a server, it's actually not sufficient for there to be the return address and the IP address of the destination. I also need to specify what type of information is inside this envelope, or equivalently, what kind of service I'm trying to contact. And I could do this by specifying in words what's inside this envelope. Maybe it's something like HTTP, the prefix that you're familiar with from the web. Maybe it's an email. Maybe it's a chat message or the like. But if it is, in fact, something like HTTP, turns out the convention is not to use words, but to use numbers. And so, in fact, I need to put one other piece of information on this envelope, which is a so-called port number, a TCP port number, which is numerically printed after a colon on a virtual envelope like this. And in this case, I wrote 80, because 80 happens to be, by human convention, the number we humans agreed on some years ago identifies web services on servers. But this means that if the server I'm sending this to, 1.2.3.4, actually has other services on it, like a chat server and an email server and the like, this won't get confused with an email that I or someone else am sending to the server, or a chat message. The server will know upon receipt of this, oh, this is a request for a web page. Let me send this virtual envelope to the web server. But HTTP isn't the only such protocol or application you can use. There are so many others as well. All right, hopefully it's not too awkward to splice that in.
We'll see.
Movie magic. OK, I'm happy if you're happy. All right, thank you. Yes? Thank you so much for tuning in. If you're still actually tuning in just a few weeks' time, we'll have this and more material online after we work some magic and cover up some of my technical difficulties. This is what it's sometimes like here behind the scenes. Hope you can join us perhaps sometime in Cambridge for this and more of CS50.